Good morning, dear students. I welcome you again in the lecture series of the subject that is 303-106-103, that is triple E. This is the lecture number 2, and we are discussing the sums of the DC circuits. In the lecture number 1, we had discussed the sum related to the Thevenin's theorem. Now, in this lecture, we will solve the same sum using the Norton's theorem. So, let's see that sum. Find out the current through 1 ohm resistance by using Norton's theorem. So this is the figure. Between A and C 2 ohm resistance is connected. Between C and B 2 ohm resistance is connected. Between C and D 1 volt battery is connected. Between A and D 3 ohm. Between A and D 1 amps current source is connected. Between B and D 2 ohm resistance is connected. And the load resistance is connected between point A and B, and RL is equal to 1 ohm. So we are interested in finding the current through this load resistance of 1 ohm, which is connected between node A and B using Norton's theorem. So in case of the Norton's theorem, its steps are very much similar to that of Thevenin's theorem. In Norton's theorem, we will also find out the Norton's equivalent resistance, which is seen between the node A and B by removing the load resistance. We will remove the load resistance and we will see the network between the point A and B, and we will find out the equivalent resistance between the node A and B, and at the same time we will make the energy sources 0. So if there is a voltage source, then voltage source is replaced by the short circuit. If there is a current source, then current source is replaced by the open circuit. So see, in the first lecture, while using the Thevenin's theorem, we had obtained the Thevenin's equivalent resistance, and that is equal to the Norton's equivalent resistance. Right, so there is no need to find again the Norton's equivalent resistance, which is seen between node A and B. Right, so recall in the first lecture we had obtained Thevenin's equivalent resistance RTH. So we had removed the load resistance between node A and B. Right, and this was our circuit. Right, this voltage, there is a voltage source, there is a voltage source. So both the voltage sources are replaced by the short circuit in the equivalent circuit. So this is short circuit, this is short circuit. Remaining circuit remains same as it is. Right, now again redraw this circuit. First of all, place the principal node. So principal node is A, B, and C and D both are short circuited. So C and D both are the same nodes, C and D. Right, so now one by one connect the resistance which are available between the various nodes. So between A and C 2 ohm resistance, A and C 2 ohm resistance, between A and D 3 ohm resistance, between A and D 3 ohm resistance. Now between B and C 2 ohm resistance, B and C 2 ohm resistance, B and D 2 ohm resistance, B and D 2 ohm resistance. Right, now these 2 ohm and 3 ohm are connected in parallel. These 2 ohm and these 2 ohm are connected in parallel, so its equivalent is 1 ohm. This is 6 upon 5 ohm, and ultimately between A and B, this is 1.2 ohm, this is 1 ohm, both are connected in series. So between A and B, 2.2 ohm equivalent resistance is obtained, which is the Thevenin's equivalent voltage, and it is also the Norton's equivalent resistance, sorry, not voltage, resistance, Thevenin's equivalent resistance, and it is equal to the Norton's equivalent resistance between node A and node B. Right, now we will apply the Norton's theorem. Okay, so here it is written RTH is equal to RN. Right, now step number 2, we have to find the Norton's equivalent current, which is designated as IN, which is also called as ISC, short circuit current, which is also called as IAB. So in case of the Norton's theorem, we remove the load resistance. After we remove the load resistance, we apply the short circuit between the terminals A and B. Right? So A and B are shorted after removing the load resistance. So this is the equivalent circuit. Right? After shorting the A and B terminal, the remaining circuit remains same, no problem. Right? Now our aim is to find out the ISC, that is IAB, and that is IN, Norton's equivalent current. So again, now there is a mesh number 1, that is ACDA. In mesh number 1, I1 current is flowing in clockwise direction. Then mesh number 2, it is CBDC. We assume that I2 is flowing in clockwise direction. Now there is a mesh number 3, which is a closed circuit, and it is what? This A to B, B to 2 ohm, C to A. So this is the mesh number 3, and in mesh number 3 I assume that current is flowing in clockwise direction, and that is I3. So now there are 3 meshes, so there will be 3 mesh current equations. We are interested in obtaining the value of I3, which is the IN, Norton's equivalent current. So there are 3 meshes. Now mesh current equation for the first mesh, it is R11 I1, so it is a main diagonal entry, so it is always plus or minus R12 I2 plus or minus R13 I3 is equal to plus or minus V1. Now R11 is the sum of the resistances in first mesh, so it is 3 plus 2, it is 5 I1. Then R12, sum of the resistance is common in first mesh and second mesh, there is no resistance, so it is 0 I2, plus R13, sum of the resistance is common to first and third mesh, so it is 2 I3. Now we have to put plus or minus sign for R13, it means for this 2 ohm resistance. Now through this 2 ohm resistance, I1 is flowing from A to C, and I3 is flowing from C to A, and the direction of I1 and I3 through the 2 ohm resistance are opposite to each other. That's why we put the negative sign. So it is minus 2 I3. It is equal to plus or minus V1. Algebraic addition of the voltages in the first mesh. So there is 3 volt and there is 1 volt. Again, if I consider only 3 volt and if I don't consider 1 volt, then this 3 volt will supply the current in a clockwise direction from positive to A to C, C to D, D to negative to A. It means in clockwise direction. And direction of I1 is also clockwise. So both the directions are same. That's why we put positive sign for 3 volt and for 1 volt. Now I don't consider 3 volt. So if there is only 1 volt supply, then 1 volt supply would supply the current from positive to C, C to A to 3 ohm resistance, to positive, to negative, to D, to negative of the battery. So current supplied will be in a anti-clockwise direction, whereas the direction of I1 is clockwise. So both the directions are opposite to each other. That's why we put negative sign for 1 volt. So this is the algebraic addition So it is 3 minus 1. So simplify this, we obtain this equation 5i1 plus 0 minus 2i3 is equal to 2. Equation number 7. Now mesh current equation for mesh number 2, plus or minus R21I1 plus R22I2, it is a main diagonal entry, so it is always plus or minus R23I3 is equal to plus or minus V2. Now recall the fact that R21 and R12 both are same, so it is 0. Now R22, sum of the resistance is in the second mesh, so it is 2 plus 2, it is 4 I2 plus or minus R23, sum of the resistance is common to second mesh and third mesh, so it is 2, so it is 2 I3. Now positive and negative. Again consider this 2 ohm resistance. Through this 2 ohm resistance, I2 is flowing in downward direction, I3 is flowing in upward direction. Both the directions are opposite to each other, that's why we put negative sign. Minus 2 I3. It is equal to plus or minus V2, sum of the voltages in second mesh. So only 1 volt source is available. Now 1 volt source will supply the current from positive to C, C to 2 ohm, 2 ohm to B, B to 2 ohm to D, D to negative of supply. It means it supplies the current in a clockwise direction. And the assumed direction of I2 is also clockwise. So as both the directions are same, we consider the positive sign for 1 volt. Positive sign for 1 volt. Simplify this, we obtain this equation number 8. Now write the mesh current equation for the mesh number 3. And the generalized equation is plus or minus R31I1 plus or minus R32I2 plus R33I3. It is a main diagonal entry, so it is always plus. It is equal to plus or minus V3. Now R31 and R13 both are same, so R13I3 it is minus 2, right? So this is minus 2 I1. Now plus or minus R32 and R23 both are same. R23 this, so minus 2. So minus 2, take the sign, right? Take the sign also. Minus 2 I2 plus R33, sum of the resistances in mesh number 3. Where is the mesh? This is the mesh number 3. So 2 plus 2, so it is 4I3. It is 4I3. It is equal to plus or minus V3, sum of the voltages in third mesh. Now third mesh does not contain any voltage source, so it is 0. It is 0. So this is the equation number 9. Right. So arrange the equation number 7, 8 and 9 in terms of matrix. Right. This R11, R12, R13, R21, R22, R23, R31, R32, R33, they are the coefficient. So it's a coefficient matrix. So separate them out. Right. So this R11 is a 5, then 0, then minus 2, 5, 0, minus 2, then second row 0, 4, minus 2, 0, 4, minus 2, and then third row minus 2, and 4. Then this variable vector, column vector I1, I2 and I3, and it is equal to RHS vector, column vector 1, then 2, then 1, then 0, 2, 1, 0. Right. So this is nothing but equal to AX. AX is equal to B. So X is equal to A inverse. This matrix is taken over here. So it's inverse into B. Right. I have done this. I1, I2, I3. It is equal to inverse of this matrix into this column vector 2, 1, 0. You can use a scientific calculator to get the inverse of this matrix and then multiply this inverse of matrix by this column vector. So this is 3 cross 3, this is 3 cross 1, so answer would be 3 cross 1. So you obtain I1 as 0.6364 amps, I2 as 0.5455 amps and I3 as 0.5909 amps. As I told earlier, this we are interested in finding ISC, that is IAB current which is flowing from A to B, and that is equal to I3. So ISC or Norton's equivalent current is I3 and I3 is this much, 0.5909 amps. Right, so we have obtained the Norton's equivalent current, we had already obtained the Norton's equivalent resistance. So finally we can draw the Norton's equivalent circuit diagram. So last step, Norton's equivalent circuit. So it consists of the Norton's equivalent current source, that is I3, that is IN, and it is 0.5909 amps, direction is upward. Then we connect the Norton's equivalent resistance, that is RAB or RN, in parallel with the Norton's equivalent current source. So RN is connected in parallel with this source, right? So this much is the Norton's equivalent circuit diagram, right? So our original circuit diagram was yes, this much, right? So this part is replaced by the Norton's equivalent current source in parallel with the Norton's equivalent resistance, and right, then finally connect the load resistance between the terminal A and B. We had initially removed the load resistance from between A and B, now connect it. So current through the load resistance is IL, right? Now there is one current source, so using the formula you can find the current through the load resistance IL, and that is equal to what? IN, total current, into we want to find out the IL through RL, so take the opposite resistance, that is RN upon total resistance, RN plus RL. So all values are known, IN is 0.5909, RN is 2.2 upon 2.2 plus RL is 1 ohm. Simplify this, you obtain IL 0.4062 amps, and direction of current, right, it is in downward direction, current is flowing from A to B, right? So obviously the current source is like this, so current flows like this and then A to B, or in other words we have obtained the positive answer of the IL, right? So current flows from A to B, so this is the magnitude and this is the direction of the current, so this is the answer. And you can notice that we obtain the same answer, right? If you use the Thevenin's theorem, or if you use the Norton's theorem, or if you use the superposition theorem, in all the methods you will get the same answer, right? Okay, so this was all about the Norton's theorem. Thank you.